we present optimization-free style transfer for 3D Gaussian splats. Several previous works have tackled style transfer for 3D Gaussian splats. Style Splat uses masked images to apply style transfer to specific objects in a scene. SGSST achieves very high quality results with fine details, but both methods require rerunning the full reconstruction process with style information, making them very slow. SGSST in particular reported training times exceeding 1 day on a GPU. Other works like G-Style and Style Gaussian have aimed to speed this up, but G-Style still requires fine-tuning the Gaussian splat reconstruction, and Style Gaussian requires training a separate feature extraction network for each scene. As a further challenge, as 3D Gaussian splats are increasingly distributed as .ply files or .splat files, they won't have the original camera images or colmap data with them. So applying existing style transfer methods to these files will require some user expertise in using a virtual camera setup and configuration. So this raises the question we try to answer. Can we style transfer a Gaussian splat without restarting reconstruction and while working directly on the splat representation? Thus, we present optimization-free style transfer for 3D Gaussian splats. Our method operates directly on the native .splat files with no retraining, no optimization, and no camera data required by using a surface-based style transfer approach. Our method is also very practical and runs in under 2 minutes even on standard CPU-based hardware. Our method builds on our prior work called interpolated selection conv, which uses a surface-based graph convolution operator that approximates CNN style operations across the surface. We previously demonstrated that this works for 360-degree images and meshes. When adapting this to 3D Gaussian splats, there are 2 key differences. The first is that there is no explicit surface. Unlike meshes, 3D Gaussian splats have no defined boundary. The other problem is that the number of points are sparse compared to a mesh or a point cloud. So we present 2 adaptations to handle these differences. First, we found that standard point cloud normal estimators like the ball pivot algorithm were able to approximate the normals well because we found splats congregate towards the surface and make an implicit boundary. We also sample the Gaussians themselves directly to create a higher density point cloud when we reconstruct our graph. So our full pipeline is to take a 3DGS scene, sample the Gaussians to create a high-density point cloud, use a normal estimation algorithm to create a graph using KNN edges and local planar projection across the normal and the edges, and then we apply our graph convolution operator to approximate this surface-based style transfer, giving our final results. So, for example, we can take this 3GS model taken from a public repository online, and we can apply a style transfer image to it. Here is another visual showing the result with the full video. We also compared our approach to the other post-reconstruction methods. We find that we have similar color alignment and style quality. And more importantly, we find that we are significantly faster in our runtime, even on CPU-based hardware. Because again, this relies entirely on the graph construction and a simple CNN model that can run quickly on a CPU. Here's more results showing our timing versus splat size. And again, for very small models, we can run in times under even 10 seconds. So we hope this method makes style transfer fast, simple, and accessible to the growing ecosystem of publicly available Gaussian splat scenes. Thank you.